All right, guys. So this is going to be probably the shortest lecture or presentation so far, and this is going to be to combine the position, velocity, acceleration, and force relationship. So now we're going to draw into play how to do this both quantitatively and qualitatively. The PVAF relationship is more of a qualitative measure than quantitative, but you can do it each way, which helps us identify how people move. So this outline real quick. So we're going to review some terms, and these are basic terms that you should already know, given the first four lectures. We're going to talk about a little bit of the quantitative approach. I'm going to show you this actually in class more, how to do the quantitative approach, because it's easier to do it with an Excel document in class. So we'll do that in class for the most part. But then we'll go over a little bit of the qualitative approach, and this is really where I'm going to ask you guys to be able to do a PVA relationship, and then we'll talk about some of the applications of in preparation for class, where I'm actually going to have you practice quite a bit, and your quiz is going to be for you to create just one PVA relationship with the F included to it. But here we have our terms to know. So we have our position, velocity, acceleration, right? So position, you'll find it either referred to as P, D, or S, depending on what orientation you have. But it's basically the location space relative to that reference point. And I can't stress to you enough this importance of reference point when it comes to biomechanical analysis, because it tells us everything. It tells us where we're going in motion-wise, and how to quantitatively compare apples and oranges, right? So direction dependent in the units of measurement. There you have numerous units of measurement. So I'm kind of going to speed through this part because you should already know this information, right? So velocity is the V. Rate change of position. Again, it's direction dependent. This is a vector, right? So we're going to be dealing with orientation relative to that reference point. And again, here you have your units of measurements, or some sort of whatever your measure of length is with respect to whatever your time is. So it's whether it's seconds, hours, or minutes. That is your time orientation. And then we have acceleration. So acceleration is the last of the PVA that we use, right? So these three are all the kinematic terms. So rate, change, and velocity. Again, it's direction independent, sorry about that, remember. So this is just in reference to whether you're increasing or decreasing velocity, not whether you're going back to or towards the origin or away from the origin. So that's why it's direction independent. And again, so now you have velocity per unit of time again. So big general usage is meters per second squared, or meters per second, which is gravitational units. So to go into further now, we bring in that kinetic components, and that's the force, or the F of this PVA-F relationship. So remember, a force is a push or pull that tends to cause the motion. And here I put the equation summation of forces equals mass times acceleration, and I put this here so you can truly see that relationship, right? So if I have the acceleration from my PVA relationship, the force component should look very similar to the acceleration profile, with one difference, and that's the mass. So you're going to multiply the mass of the individual times every data point acceleration, and basically you're going to have the same motion, or the same frequency of movement, but the amplitudes at each one are going to be different. So you're going to have a greater magnitude of the y component of it for every x component of your graph, right? So mass is the important connection between your acceleration profile and your force profile. So the other terms to know, in the biggest connection, and we'll show this in a second, is slope. And what is slope? Well, slope is simply the rise over run, or the change in the y over the change in x. And its discussion describes the direction of change and the steepness of change from each of the x points along the line. Now, what's most important for us, what type of slope is most important, is going to be the tangent. And the tangent is that straight line that touches the graph in one point, and right. So this deals with the infinitesimal small change in position across that. And I'll show you a little bit of this in class, where we do the slope of the line with the pen, and that tells us. So the tangent, you bring your change in t as small as possible to where your line only touches at that instantaneous point along the line. Some other terms to know are derivative and integral. Now this is that mathematical term that we use, and just know that derivative, you're talking about the slope. Integral, you're talking about the area under the curve. Derivative is when you go from P to V to A to F. Integral is when you go the opposite way. So when you go to F to A to V to P. For this class, we're mainly just going to worry about derivatives because it's a little simpler. And I just want you to understand the relation between the four. And we're going to do that mostly with the derivative, or the rate at which the value of function changes with respect to another value. So it's that slope along the line. So here is your relationship in kind of a graphical or a picture depiction of how it's all working. So here we go. So you have position, you want to go to velocity, and then you want to go to acceleration, and imagine the forces of the other side. Well, you do that by doing the slope, and that's your derivative. To go the other way, you do the area under the curve, and that's your integral, right? So this is that PVA relationship. Just throw the F on the end, it's the same connection, right? So you have all four of them. But to go from left to right, you do the slope. To go to right to left, you do the area under the curve. And that's simply the relationship. Now we're going to just show you some easy ways to do it. So if I wanted to calculate this from a quantitative perspective, you do that simple change in rise of change in run, right? So you're going to use the instantaneous velocity, instantaneous acceleration, all those to actually do the calculations, right? Because if I want to find out what the rise over run is at frame 5, I need to use frame 4 and frame 6. So the important aspect that quantitatively, time rate of change, we're going to use instantaneous measures, not average. Okay. Now, when we do it graphically and qualitatively, this is going to be the relationship you follow. We're going to identify critical events, and it's going to be from this is the rule. You have IP, go to minimum max, which goes to 0. What does this mean? Well, IP is the inflection points, so it's a change in the direction of the slope, and you'll see this easier in class because I'll show you how to identify that. But it's essentially the change in concavity. So it's where the slope changes from either increasing to decreasing or decreasing to increasing, right? So it becomes more steep, and then at some point it changes and begins to become a flatter, or the opposite way. So this is where that IP is, right? So it's from the max steepness. It's essentially identifying max steepness, and that's why it's a min or a max. Now, what identifies whether it becomes a min or a max? Well, that's the polarity of which. So if it's a negative or a positive, if it's a negative, it becomes a min in the next graph. If it's a positive, it becomes a max in the next graph. So the important thing to understand about a min and max is it's a local min and max. So the same graph, you can have multiple mins and multiple maxes because you're taking little chunks along your graph or your plot to identify what's happening. And again, so the slope of the tangent, the slope of the line there is 0. So the rise over the run, the rise is 0. So that's why it's a min or a max. Now that's why it becomes a 0 in the next. So there's no rate of change, right? So a min or a max becomes a 0 because the slope of the line at that tangent is 0. So there's no rise over run. So this is what it looks like graphically. So this is a very traditional center of mass vertical oscillation during running. On the y-axis, I have position in meters. On the x-axis, I have time. So if you look at that, you can figure out the sampling rate by the change in time. But if you look at this, you want to look at the inflection point. So inflection points, again, think about it, is where the slope is at its steepest along the line. And now what we're going to do is we're going to break this up into little chunks. And so if I looked at the inflection point from this, I would calculate, these are all inflection points with the pink you see here. Now, one of the things that's important to understand with this is we're doing it graphically. So we're not going to calculate the instantaneous. If you want to do it quantitative, you can. I'll show you how to do that in class. But from a graphical perspective, in a qualitative perspective, we are just going to put these along the line so where we anticipate there being a change in concavity. And you can see the concaves up and down here, but it's a change where the line is at its steepest. Now, what it's hard to see is there's also 2 here on the outside in the green. So that's the idea, is you have to go all the way out. So we're going to use our rules in what we know about motion to help us do this. So in this graph here, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 inflection points. Now, the inflection points become the min and maxes in the next graph, which would be the velocity graph. And to identify those, the first green one is a positive, the first pink is a negative, and you fluctuate back and forth on this graph with those. And hopefully you see that, and we'll go over that more in class. So if you have a question on that, make sure you ask the class so I can make sure that everybody sees that. Now, all the reds here are the local maxes, and all the purples are local minimums. And hopefully you see that, right? So they're maxes because they're the highest y values, and they're minimums because they're the lowest y values. Now, there is no difference in what maxes and minimums become in the next graph. So they all become the same item or critical point in the velocity graph, and that's a 0. So all those become zeros in the next graph. So graphing, and I'm going to walk you through this in class. And so what's going to happen is your quiz is not going to happen until class, because I want to show everybody how to do this setup. So in class, everybody's going to have a piece of graph paper, so bring a pencil and bring a ruler if you have one. Otherwise, you can do it freehand. But I'm going to show you how to do this, and everybody's going to take the quiz this week in class. So set up the graphs in a vertical alignment, and I'll show you how to do that temporally. So you stack the PVA and velocity or force vertically. You always have to label your axes. If you don't label axes, you don't know what you're doing, and I can't give you credit. Okay, so you're going to lose some credit if you don't have the axis labeled. Like in my previous one, I had position and I had time. And then because this is how you're going to identify the origin. What does the origin identify? And that's where you're going to come with this, right? So what this means is the origin is going to be either the ground, or if I'm jumping from a cliff, is it the cliff or is it the ground that I'm jumping to? So these are very important identifiers when you talk about the position. So you need to clarify what the origin is in your process. And this goes from understanding how things work. So you always begin with the known. So what information is given, your previous knowledge of the task, and then you separate it into sections if possible. So when somebody gives you something to do a PVA, and when you identify the motion of the cycling, the knee during cycling, when you identify the center of mass motion during running, or the knee flexion during running, you need to know what's known and you need to know what's not known. That will help you in the process because it helps you chunk out the different phases. But then you also break the graph into section, and that's what I'm just talking about with those phases, is you use vertical lines to connect critical events between the graphs. So because they're stacked on top of each other, I can take the critical events like a min or max, and I draw a dotted line down to the other ones, and that's going to help me identify where to put this concept in the next graph. And we're going to go over that a lot in detail in class, okay? So just a summary, to derive graphs, you use a slope, and to integrate them, you use area in the curve. And for our purposes, we're going to focus on slopes, just so you can see the relationship from going from one to the next. I'll briefly show you integrating graphs in class, but for your purposes, make sure you know deriving graphs. The critical event in how to get from one graph to the next is inflection points, min, maxes, and zeros. And these essentially are dealing with the slope of the line at that point. And again, this is with deriving. And then the important aspect of when you're doing the graphical representations of these is to align your graphs vertically and draw lines connecting them. And I'm going to show you how this works too with the quantitative graphs that I've created with Excel. And we'll do that so I can show you how they actually do line up on the process. Okay, so make sure you come to class on next Friday and ready to take the quiz, because the quiz is going to happen in class. So if you don't show up this week, you don't get the quiz. And I know if you didn't listen to this all the way through, because you'll send me an email asking about the quiz. So have a good week, and we'll have some fun on Friday.